Today we will continue with some application of integral, and we'll study some things related to physics. We'll study work. So suppose we applied a force to an object, right? And the force is, according to Newton's law, it is m times a, where m is the weight of the object. A is the acceleration. And you can look at the funny picture here. I found it interesting. I don't know if you think about it, but it's yeah. So the unit of the force, we use kg for the weight, kilogram. And the displacement, we use it in meters. The times is in seconds. So the unit of force is Newton. 1 Newton is 1 kg times 1 meters over seconds square, because m over second square is the unit of the acceleration. Okay, it's fine. And this terms is the work done. It will be the force we used to make a movement on the object. And suppose the force we applied to the object is F, and the object is moved a distance d, then the work done will be the product of force and distance here. Therefore, the unit of this will be Newton meters, or we call it joule here. Okay. In the US, we use a different system. For force, we may use pounds, foot pounds unit, which is about 1.36 joule. So the US is powerful, right? So we use our own system, but elsewhere in the world, we normally use kilometers for distance, and yeah, kg for weight. Here's different, a little different. It's fine. So, and let us take a look at the first example. We want to compute the work done when we lift an object whose weight is about 1.2 kg to the height 0.7. You can see it on the notes here. The acceleration, we use it gravity force, which is 9.8 meters per second. Okay. Because, yeah. The same questions, but we find the work done in different unit. Foot pounds here. Okay. Remember, we have the formula. Force is given by this. It's MA, and the work done is F and T, right? So these are the formula we need to use. Okay. So when we write all things given, first, the book is 1.2 kg, right? Which means we are given that M is 1.2 kg. Is that okay? What else do we need to find? And what else are we given? We're given M, right? And the acceleration here we computed, and it is given here. A, in this case, is equal to g, which is the acceleration of gravity. And it is given that 9.8 meters per second square. This is the second thing is given. So it means that we can compute F, right? So therefore, what is F here? What is it? Help me, please. Yeah, 1.2 times 9.8, which gives us 11.76, and the unit of this is Newton. So we need to find the force, work done, right? We have just found F here, and yeah, we are also given that D, the distance, is 0.7, right? Meters. These are things we are given. Okay. So, therefore, what do we have here? Very good. Thank you, Rami. Right. And this product gives you the number 8.2 joule. Okay. These kinds of, yeah. Yeah, we need to use this unit. If they are not in this unit, we need to change it. If we're given in kilometers, we need to change to meters. Right? Yeah, we will. The work done, we will always need to compute it in Newton and Joule here. Okay. Very good question. And in the second question, right, the same story. Now, how much work's done in lifting this much 6 foot, right? So we're given that a weight is 20 pounds, okay? And the distance is 6 feet, right? So we use different system in the US system. So in the question B, so the force, the work done is W, is the same formula. But now we compute it in pounds, foot pounds, which is F is given that 20. The distance is 6 feet, okay? Therefore, it will be 120 feet pounds unit. So that's it. In this example, we suppose that the object is a point, right? It moves some specific distance. But now suppose that the total work done at each position when we apply a force on an object. Here, if the force, now we consider it as a variable, and it moves along the x-axis here. In the positive direction, remember, we're considering it in the positive direction. From x is equal to A to B. Okay, let us draw a picture of this. Okay, according to this, suppose the origin is here, right? Then the object is moving from A to B here. Right. And at each position F here, the force is F of x. The force is a function depending on the position of this. Okay. We divide this intervals into subdomains. It means that at each position on this intervals, we apply a force F at xi, right? The total work done in the whole domains here, it will be the integral, will be the product, the sum of the product for the all points xi, where xi is a sub-intervals in this intervals. So the same ideas remain sum. The work done of the force from A to B is given by this formula. Okay. That is the integral from A to B. Keep in mind that the direction of moving and the origin and the x direction is the same. Otherwise, we need to change the sign. But now, let us consider another example. If a particle is located a distance x from the origin, okay, let us draw it down. This is the origin. Okay. And the force is x squared plus 2x and the force from this on this intervals is given by this equation. So we know that force will be applied on the whole intervals here, right? The same direction. Then the work done of all these particles will be the integral from 1 to 3 of the force here. The force here. Where it is given that F is x squared plus 2x dx. Okay. This becomes an easy integral. We can compute it easily. And what do we have here? We need to find the antiderivative of these two guys, right? In order to do the antiderivative, this is x squared, then antiderivative of this will be x to this power, and we need to, what should we do here? Add 1, right? Then need to multiply with a fraction whose number's denominator. Whose denominator is exactly this power, which is 2 plus 1. Very good. The same things applied here, right? But we take the integral, we can ignore the number 2 here. We just rewrite it. Okay, the constant, it does not affect. So we just rewrite it here. But then we need to find the integral of x here, antiderivative of x, which is x to the 1. We need to add 1 here, right? The same story, we need to multiply with a fraction whose denominator is exactly the power here, which is 1 plus 1. And remember, we are taking the definite integral from x is equal to 1 to x is equal to 3. This will give us a number, right? So before doing this, let us simplify these numbers. It is 1/3 x cubed plus, what do we have here? 1 times 1/2. They will cancel each other, right? So it would be What do we have? Yeah, x squared. We can double check it by taking the derivative of this guy. If it gives us the same result as the integrand here, then we're good. This is, we need to evaluate the upper limit first, okay? To avoid mistake, let us write the whole function here with the evaluation of x is equal to 3, which is 1/3 times 3 cubed, right? And 3 squared. This is the first term, parentheses. Subtract the lower limit here, which is okay. Now it becomes easier. We just simplify it. 3 cubed divided by 3 give us 3 squared, which is 9. Here is 3 squared again. Then it is 9. Subtract here is 1/3 plus 1. Okay. So we find the common denominator so that we can add them up. It becomes 18 minus 4/3. Okay. Then finally, it gives us 3 times 18 minus 4 divided by 3, which is 50/3. Okay. Well, this kind of problem is not very difficult, but we need to understand how to establish, to set up an integral here, right? Now, we do another example. This is the Hooke's law. It states that if we are given a spring here, and this is the balance position at 0, the initial position, yeah, balance, no stretch, no strain. If we pull this object to the positive direction, the same direction with the x-axis, right, like this, and it is stretched. And this, the distance, the displacement is, suppose it is x, right? From 0 move to x, then the force would be k times x, the Hooke's law. Okay? And x here is very small. If it is large, then we need to use a bit different formula. So k here, we call it the spring constant. Okay, it is a positive number. So we have the formula, right? And the work done. The work done here, yeah, let us see. Now we consider this example. If the force is 40 Newton, we apply to stretch an object here. Let us say, suppose the object is this is the x direction. This is the spring. Right, the object is here. Suppose this is the 0 position. Then it is pulled this way. It is stretched up to here, right? This is 15 centimeters. Okay. Then they ask us to compute the work done. When, in order to make it stretch up to this position, to 18. Okay. So since we are given the Hooke's law, remember that the Hooke's law satisfying this equation. Force is K times X. Okay. Now, according to the problems here, we're given that, what are we given? Yeah, the force F, right, is 40 Newton. What else? Yes, 50 centimeters, right? It means that we're given the displacement X here is 15. Okay? Oh, wait. The natural length of the spring is 10. Okay, it means here it should be 10. This is the origin, I'm sorry. This is the natural length of the spring. So it means that the movement from the distance from here to here will be 5 centimeters. Okay? Therefore, 18 should be somewhere here. Yeah. So from this relation, what can we do? What does it tell us about? It would tell us the K, right? So in order to find K, what should we do? From this formula. Thank you, very good. And F and X were given, right? Which is 40 over 15, is it right? Oh no, X here is 5. The distance from 15 to 10, right? Is it 40 over 5? Very good. We need to take into account the unit. This is in centimeters. So we need to change it to meters, right? And 5 centimeters will be, what is it in meters? 5, 10 times 10 to the minus 2 meters, okay? Because 1 meters is 100 centimeters. Very good. So it will be 0.05. Very good. Or if you do this, you can write it 40. 40 is 4 times 10, right? This is 5. Yeah, let us write 40. 40. And here 5, 10, 10 to the minus 2. So the number 10 to the minus 2, we can bring it up to the numerator, right? And this is 40 divided by 5 times 10 to the 2, right? It will be 80. 40 divided by 5 gives us 8. And here is 10 squared gives us 800. Okay, that is the K. Or you can simply use your calculator. So we are given K already, right? We are given K. Now, if we want to compute the force applying to this distance, right? The force, it means that, so the work done would be the integral from this distance to 18, right? And we need to write them in dx, where x, the initial distance, it will be from 5, 10 to the minus 2. Yeah. And the next position, it will be from 8 to the 10 minus 2. Force times dx. It's a little hard to see, but is that okay now? Okay. Then, having everything, we can compute it easily. It is 5, 10 to the minus 2 to 8, 10 to the minus 2. F of x here will be k times x dx. And we found k already, 0.05, 800 x dx. Okay. So the numbers is easy. So antiderivative of x is what is it in the denominator here? Yeah. And we're evaluating this from x is equal to 0.05 to x is 0.08, right? Yeah, go home and compute it. We will be able to find it would be 400 times x squared. X is, oh yeah, use this one. 0.05. And it will be 1.56 joule. Okay. Do you have any question? Then another example will be a 200-pound cable is 100. Oh, interesting. Is 100 feet long and hangs vertically from the top of a tall building. How much work done? How much work is required to lift the cable to the top of the building? Okay. Now let us draw it, visualize it. The work done here is the work done by the gravity, right? Because it's hanging here on the top of the building. Suppose the building is like this. The height of this building is 100 feet. So there, let us place the origin is right here on the top of the building. And the cable is very thick. This one, it's not very that big, but yeah, suppose it is like this. Okay. Gravity, right? G is equal to 9.8. Yeah, something. Okay, now we need to compute the work. Yeah, this problem is confusing. Okay, the force, apply this, work done. Yeah, the force. How to draw it. So now, if the interval here, we call the intervals xi, and the sample point xi star is belong to this intervals. We discretize the domain in X into small intervals. Okay. So now the total weight of the cable is, how much do we have here? 200 pounds, right? It means that at each point here, we divided by, okay, how to say it? The total weight is 200, and the length of this cable is 100 feet, right? So the weight at each position here, right, would be the fraction at the I part. So the weight of the I part is, we average it. It will be 200 divided by 100 feet, right? Okay, which is 2. Right? That is a point on this cable. That is 1 point. So therefore, the part this is the point. So therefore, let us find the weight of this interval, right? Of the cable in this interval. It will be this much, right? 2 times delta xi. Okay. And it will be, and delta xi is, the unit of this is in feet, right? So if we multiply here with feet, the unit of this will be 2 pounds divided by feet, and multiply with feet. So feet and feet here will cancel each other. So give us the weight, right? Makes sense. So the weight of this part is like this. Okay. Therefore, the same principle. The work done will be the integral from origin to this. The whole cable is from 0 to 100. Right? And we discretize this in end intervals, right? Multiply with the xi here, we have that it is 2 times the point, the position x dx, right? So, and finally, this is hard, but this is how we do it. This becomes an easy integral. We can find it. So therefore, yeah, I think you can go home and find the solution of this one. Yeah, you have a good one and see you tomorrow.